Quiet summer night in Central Europe. This chicken coop is a safe home for our poultry, but it wasn't like that before. Some time ago we had 10 chicken and a rooster. Suddenly one day we found out that 6 of them went missing, and it seems like some predator came and have dramatically decimated their population. To prevent such unpleasant surprises, one can use automatic coop door because foxes usually attack during nights. Here is a quick review what you can find on internet. Cheap Chinese automatic coop door, winch-based door opener, but it doesn't look very reliable to me, and door opener of the same brand but with linear actuator. All of them use light sensor or clock to trigger opening or closing. The sensor can easily get dirty, and alarm clock with fixed times is also not a solution unless you want to update the alarm times every 2 weeks to reflect changing sunrise and sunset times. So I decided to design my own solution based on slightly different approach. The most critical part is the actuator, and since microcontrollers are not powerful enough to control the actuator directly, we will need a device called driver. In our case DRV8833 with sleep function, which is crucial to keep the overall device consumption low. Brand of this project will be this Arduino Pro mini board from DF Robot. Contrary to other minimalistic Atmel boards, this one can be programmed directly with standard ICSP header. To keep track of the time, PCF8563 is used. And finally we will need LCD display with HT1621 controller and encoder. If you have ever tried to design user interface application on Arduino based project, you know how difficult it is. Write code, compile, flash it on the board over UART or ICSP, test it, fix the code, compile, flash, all over and over again. But what if we design all logic and user interface code to be completely independent from the Arduino's ecosystem and test it in some virtual environment? Arduino uses C++, and C++ can be compiled as desktop application, and by emulating the display, RTC clock and encoder, we can quickly test and debug the code before deploying it on Arduino board. But what framework to use? For unit test, we have old good Google test framework, but what to choose for interactive tests? SDL2, Qt, Cocoa? No, we have something much better, webassembly in combination with HTML5 and JavaScript. What you can see now is the same code as the code running on the Arduino. The display is emulated with some CSS magic I've borrowed from GitHub user named Grezzo. Instead of rotary encoder we have 4 buttons, one emulating short click, another for long click, and 2 for turning the knob left or right. By holding the rotary encoder knob, you enter the configuration mode. Here you can set the time, date, year, geographical coordinates, time offsets in minutes for postponing the opening after sunrise or closing after sunset. And you can set time zone as well. In this simulator you can alter the date and time reported to the core application by clicking on HTML buttons on the bottom of this page, or set any date or time you want. The web application nicely shows whether the door is opened or closed. The same application, but this time it is running on 8-bit Atmel microcontroller. By pushing the button we switch between automatic and manual mode, which is shown as small triangle on the left. Let's enter the configuration mode as we have seen in web application. At first we need to set hours, minutes, day, month, year, latitude, longitude. OP stands for opening offset. By providing positive number like 20, the opening procedure will be delayed by 20 minutes after sunrise, and by providing -20 for closing offset, the coop door will be closed 20 minutes before sunset. The time stored internally in RTC chip is in UTC format, because the software needs universal time for some calculations. That means we need to provide in which time zone we live. I am sure you are very curious how this cute 3D printed box looks from inside. Don't be scared, it is just a prototype. And for final solution, all of the wildly wired parts will be replaced by single board attached to the LCD display by angled pin header. From the left there is RTC chip with backup coin battery, driver is in the middle, and MCU board on the right with 6-pin ICSP connector. The top part holds 4 AA batteries, LCD display and rotary encoder. To reduce the power consumption of the LCD backlight, I replaced the resistor on the right with larger value. And under the connector there is another resistor which needs to be replaced in order to get better contrast. To finish the installation we will need few more parts. Because the actuator has mechanically preset end positions, we need to ensure that it can reach them both safely. Otherwise the motor wouldn't stop and would drain the battery. For this purpose I designed simple spring-loaded element which can retract for about 2 cm. It consists of 2 3D printed parts, steel spring and a screw. The inner part nicely fits the actuator's rod and the other just snaps in. Then there are 2 hinges, one with smaller gap which goes to the rod and one with larger gap goes to the motor housing side. That's it, let's proceed to the installation. On the right you can see simple construction with styrofoam roof protecting the IP camera. The time-lapse shown at the beginning of this video is just from this camera. At first, we will install the hinges and a piece of double-sided tape helps to keep them on place. If you were watching carefully, maybe you have noticed that there was plastic bottle cap with small hole on the table shown 1 minute ago, and I did not explain its purpose. And now, next to me there is a plastic bottle with water. I will give you a small hint. Can you hear the rooster crowing? This guy is pretty aggressive, but spraying him with water keeps him away. Today it was very hot day, so he stays hidden under the tree at safe distance. Few words to the actuator. The label says it is rated for 12 volts. It has 10 cm stroke, speed of 15 mm per second with force of 80 newtons. I tested it on laboratory power supply and it works nicely till 4 volts. We are powering it by 4 AA batteries which gives us 6 volts, which means that we are getting maybe half of the stated force. Considering the position of the hinges relative to the door, the force at the edge of the door will be below 30 newtons. That means, if a hen will be stuck in the door, there will be force smaller than 3 kg pushing to her body. It is not much and shouldn't hurt. But it's easier to set the closing offset to 30 minutes to be sure that the flock is at home before the door closes. Besides of replacing the resistor from LCD display to reduce the consumption, power LEDs from MCU board and motor driver have been removed. I was able to shrink the consumption down to 1 mA. I was planning to go even farther to remove the crystal and switch to internal RC oscillator, but consumption below 1 mA for a prototype is just fine. Now you can see the spring in action. It is very important to check if the actuator can move freely on the hinges and if it can reach both end positions without excessive force. Everything looks nice, so we can switch to automatic mode. But how does it work if it doesn't need a light sensor? Mathematics and geometry is the answer. If you know the geographic position and time, you can calculate the position of sun relative to the horizon. This video shows comparison of this algorithm with the day and night world map from website timeanddate.com. There is a grid overlay of red and green dots. If the result of the calculation is day, a green dot is displayed. When the point is red or green all the time, there is a polar night or polar day respectively. All 3D models used in this project were designed in online 3D editor called Onshape. You can find links to all models, software and other resources in video description below. This box is designed to hold together without using screws or glue. It took several times to fine-tune the shape of the teeth holding both pieces together. It is firm enough to hold together, yet still possible to open for battery replacement without the fear of breaking it. After using this device for several weeks, it stopped working. Not because the batteries were dead, but because the RTC got crazy and started reporting wrong time. I usually buy the cheapest available components from eBay, so I was expecting some defects, but I wasn't expecting that almost all RTC modules I got will be useless. To check if they are operating well, I made simple application for LA104 for reading and setting time over I2C protocol. I set all 3 modules to the same time, and after a few weeks I check them for deviation. You can see that the first module is off by almost 2 minutes and other modules are completely wrong. Maybe they were not stored properly. I noticed that it stops ticking when I touch the crystal terminals, but this is probably normal behavior in all RTC modules. I was thinking that there is some issue with date rollover circuitry, so I made a simple test which sets random day and time to midnight, waits a second and then verifies if it correctly rolled over to following day. But the question remains, what do they sell in China? Are those counterfeits, or are they just selling defective chips which would normally go into trash? And another side note, the cheapest motor driver I found is L298N. Don't buy it. It doesn't have short circuit protection and it is very easy to damage it. Then it will keep draining 30 mA even when no load is connected. If you are a hardware engineer, please let me know in comments where you buy components or if you had good or bad experience from purchasing stuff on eBay. That's all from me. Now let's enjoy the morning routine of our rooster.